And by way of proof, and this is us. I was routing AD for a while, and I've co-chaired a number of working groups, and I'm really a circuit switch traffic engineering person deep down inside. I've just become the independent stream editor for my sins. Hamian, this is brilliant. This you've got to guess the age of Hamian in this photo and compare and contrast with him now. This was his graduation some 20 years ago. Hamian's pretty active in some of the key working groups, TEAS and PCE and CCAMP, and has been a specialist in GMPLS and management for optical networks. So what we're going to do is do some tag team going through this, do some different slides each, but probably interrupt each other as well. By way of a warning, we can do nothing more in an hour than really skate over the surface of what traffic engineering is and what work the IETF has done. We'll be moving pretty fast. There are individual slides in this set that we could talk about for half an hour, but we won't. So the intention is it gives you some pointers, some IETF work to go away and look at. And obviously, if we leave out your favorite protocol, it's either because we forgot it or we don't like it. Right, so we'll break it down as what is traffic engineering and why we do it, have an overview of some IETF technologies, some of which are quite old, and then try to spend as much time, oh no, the traffic engineering working group chair has just come in at the back, so now we're really in trouble. Yeah, we'll try and introduce and spend quite a lot of time on some of the new techniques and architectures for traffic engineering. As far as references go, there are just way too many to list. What we've tried to do is pick out on many of the slides a key RFC or draft that you should start with if a technology interests you. And then at the end, we have a list of relevant working groups. So what is the point? Why traffic engineer? It's all about getting good performance out of a network and delivering additional services. So the first two bullets here are a quote from an RFC from last century, 2702. Is actually a requirements RFC for traffic engineering in an MPLS network. But what it does is set the scene by saying this is the application of technology to measurement, modeling, characterization, and control of traffic in the internet to achieve specific performance objectives. And it then goes on to not say what specific performance objectives they might be. But in summary, the purpose then is to allow you to provide more reliable traffic delivery, offer advanced services. If you're a network operator, you want to offer advanced services to your customers. You want to make better use of your network resources. So deployed resources cost money. You don't want them wasted or tied up. You want to be able to get as good a use out of your network as possible. You want to survive network outages, but also manage planned maintenance. Part of all of that is making the network predictable, so you can guess what's going to happen to your customers' traffic when there's a change in the network. What this really means is you have to know your network. You have to know the nodes and the links and how they're connected. You've got to know the capabilities of those nodes and links. largely in terms of bandwidth and delay and arbitrary metrics which are assigned to them. Oh, first typo. You need to know traffic patterns, demands, and matrices. You've got to know what traffic your network is going to carry if you're going to engineer that traffic. And you have to know what sort of errors, what likelihood of errors, and what plans you have for maintenance. Once you know all that, then you have to control how the traffic is placed on the network. And to do that, you configure the network, the traffic, and you actually configure the management tools themselves. What sort of networks are we talking about? Well, this is the IETF. So essentially, we're talking about the delivery of IP packets. Turns out that the principles of traffic engineering apply to any network that delivers commodity. So I've seen similar or identical algorithms applied to electricity networks, to the management of cars on road networks, to the delivery of water and the inverse delivery of sewage, and so on. And the sewage is fun because I used to have a company that made a sort of traffic engineering tool using machine learning. We built it for IETF protocols. Our first customer was a sewage company. What that tells you about the IETF, I don't know. Here, we're going to focus on layer 3 and below. So that's IP, MPLS, Ethernet, and then all the transport technologies that sit underneath. So it's all, well, it's nearly all some kind of circuit switching, whether it's connection-oriented or connectionless, but IP is a little bit different on top. All right, computer science networking 101, shortest path first. It's what our IGPs do. It's how we generally deliver IP traffic in the network. And it's great, except that traffic tends to converge towards certain links. And it's just a little bit hard from outside the network to know where your traffic is going for any particular flow. Along comes constraint-based shortest path first. And all this is doing is saying, not only am I interested in the cost of links, but I'm interested in additional qualities of those links. And it may be things like bandwidth availability. That's the most common one. And from a computational point of view, it's very easy. You can prune the graph before you even start. So you take out all the links that don't match your criteria, and then you run SPF. It's easy. Those computes can be end-to-end, and that's also easy. You're just running a limiting factor on SPF. So it all turns out to be really simple. In this picture, you might want to compute a path that uses only red links to get end-to-end, and that would be fine. But you would still find that if you ran your network saying everybody's interested in only red links, then the traffic would tend to converge. So this is a standard picture from traffic engineering tutorials. It's a fish. We overlay on the fish. The reason why it's a fish is because it's sort of fish-shaped graph. We overlay on it some nodes and links, and the links have bandwidth limitations. So the green ones are 10 megabit. The blue ones are 7, and the yellow ones are 5. And then we place two demands on the network. One of them is a 7 meg demand, and one's a 5 meg demand. And they're both coming in, and they're trying to get to the fish's nose. Do fish have noses? Anyone know? No, nobody knows. Do fish have noses? Yeah, okay. Virtualized nodes, yes. So suppose the 5 meg demand comes first, and it's routed on shortest path first. Well, it's going to go on the blue link. It can't help, and it's going to pick the green links to go through. And when that happens, the 7 meg demand turns up, and it can't be placed. Clearly, the network can support both demands, but not if they're they arrive in the wrong order and they're just handled as shortest path first. So what traffic engineering is all about is understanding the set of demands you're going to have, understanding your network, and causing those demands to be placed in the right way through the network. So if the 7 meg demand can be sent, the 5 meg demand rather can be sent around the yellow links, then there will be space for the 7 when it comes later. So to solve that problem, then, you need to know the topology. You need to know the status of the links. Are they up, down, paused, ready to come down for maintenance? What's the bandwidth of the link, but more importantly, what bandwidth is available and is not being taken up by other services already? Other constraints that you might be interested in, and those are increasingly delay type constraints as we start to deliver 5G services, but for optical networks, they may be the ability to convert or not convert wavelengths, and things like shared risk link groups, which are the preponderance or the likelihood of one link failing at the same time as another link fails. So if you know all of those things, and then you know the demands that are going to be placed on the network and any relationship between the demands. For example, one may be providing a backup service to another. You don't want to send them down the same link. If you know all those things, then you can do a computation that will cause you to place your traffic in the network and do clever things to make sure that you deliver services. So we need tools to do this. We need network management. The network management can see the network, and it can see the demands, and it's responsible for working out how to place the traffic and issuing instructions to the network to configure the network so that the traffic will go the right way. We need some mechanism to learn about the network, learn its status and learn its topology. And that's really a discovery process, but for various reasons, we use routing protocols to do that. We need the ability to configure the network devices, and that can be direct configuration or signaling protocols. And then as the packets go through the network, we may need to mark them so that we can tell which packet is meant to go which way through a network. And essentially, the rest of this presentation is talking about different techniques for doing those different things. You don't always end up using all of those tools at the same time. So, these are the existing IETF tools that we will run through, and then we'll have another section talking about the future ones. So we've got a slide or so on each of these. And this is where references to RFCs and drafts start coming in. There'll be little yellow boxes down the left-hand side to give you your pointers. Source routing then. Source routing is encoding information in a packet to say which path through a network a packet should take. It's essentially a series of hop identifiers, either link or node addresses, saying, right, now you've done that hop, this is the next hop to do. And that can be a strict path. A strict path is a full list. There's never any ambiguity. Whenever you have a packet in your hand, you can see this is the next thing I must do. It requires no information to be stored in the network. All of that information is placed in the packet itself. And the example, best example of this is IPv4 strict source routing option, which enables you to put in a list of, I believe, 9 IP addresses. And this is instructive, just as a side issue. When IPv4 was designed, it was clearly expected that the diameter of the internet would never be more than 9 hops. So that was a good prediction, wasn't it? IPv4 strict source routing option is generally not used. Okay, it exists, it's not used. Loose path. A loose path breaks that strict path down and says, sometimes I just want to get all the way over there. I don't need to fill in the gaps. I'll just say next hop, maybe get to the edge of the next network. So that information is still in the packet header, but it relies on the network itself to fill in the gaps using normal shortest path first routing. So it's a combination of tools then. And there are 2 examples of that. IPv4 has got the loose source routing option, and IPv6 has got a routing header extension. And apart from segment routing, which we'll come to later, neither of these options is actually used in the wild. So it's a great tool, it's just not used. Another tool is called metric tweaking, and we have 2 graphs here. They are the same topology and the same demands, a green demand and a red demand trying to cross the network. And in the top picture, if we use shortest path first routing, what we find is that both of the demands get routed across the same 2 links in the network, these 2 guys, and that potentially means that they're overloaded. So the metric tweaking approach says, well, if we just go in there and change a couple of metrics in the whole network, we can cause the demands to go differently through the network. So this is just touch these 2 metrics, and now the shortest path first, I can see you all busily checking my maths. I think it's right. They get routed differently, none of the links is overloaded. So in principle, this is a really nice technique, but you have to notice that I've done just 2 demands on a simple network. If you put 10,000 demands on a big network, this becomes an extremely interesting computational problem. You can get some very exciting, unexpected consequences. You go in and tweak 1 demand and all the traffic suddenly goes a different way. You can flat the network as you install these new metrics. And if you're doing that in a live network, I needed to change both of these. But I changed one first and all the traffic went the other way. And I've just made it even worse. And then I change the other one and the traffic comes back again. So you've got to be really, really careful. It needs a central offline tool to do all the computation, to understand the whole traffic matrix and how that's going to end up on the new network. But that really is possible and it really is deployed, and there's some tier 1 carriers who do this in their IP backbone and they still make money. They haven't screwed up. So it's entirely possible. All right, you can look at one topology, one network topology, and make multiple copies, logical copies of it. And effectively, mentally partition the network resources into multiple slices, instances of that, and build what we call colored graphs. So what the figure does is it says, look, there's a topology there, and for every link, we will give it a red metric and a blue metric, apart from I noticed that one, which is a colorblind blue metric. Second typo. I thought you reviewed these. So what it means is when you've got some traffic to inject, you can make a decision. I'm going to call this blue traffic, and it will get routed through the network on the blue graph. Or I'm going to call this red traffic, and it will go through the network on the red graph. How you actually make that decision, well, that's a local policy choice. You might make it per customer, or you might just hash the source and destination address into a bucket and say all of that traffic goes on one graph. Once you've done that, you color the packet. You use a field in the IP header or in the MPLS header, color the packet, and then it will follow that graph through the network. And the IGPs allow you to advertise the different metrics with their colors, and off you go. I've seen two principal use cases for this. One is providing resilience. So you're able to partition your network and say, if there's a failure on any link, I know that the other color network, the other color graph will be up anyway, so I've got a backup. And I've also seen one color reserved for high priority traffic. So emergency service traffic goes on the red graph, normal traffic goes on the blue graph. And in that case, the red graph is probably highly underused. Enter RSVP. RSVP is a signaling protocol. It functions by having control packets that fly around between protocol instances and are used to describe the traffic and to program the network to expect that traffic. Those control packets follow the flows, or they follow the same path that the flow will follow. So they ideally come before the traffic, but they could actually happen once the traffic is already flowing. They have the same IP addressing, so they follow exactly the same SPF path. And what they do is they go outwards describing the flow, saying, there is traffic coming here and it needs this amount of bandwidth. And then the control packets are fired back down the network saying, yeah, okay, we have a destination, we understand what's going on, now reserve some bandwidth, some buffers or whatever in the devices so that the packets can be processed. So what's going on here is there's an overhead of control message exchange, there's state needed in the network to actually reserve resources and to understand the relationship between the control messages. But it's highly adaptive to changes in the SPF. So if a link goes down and all the traffic is routed a different way, the control packets are also routed a different way. So the network quickly learns about the changes. It also handles merging of flows, which is not uncommon. You know, lots of traffic's coming from many places going to the same destination. You can start aggregating. RSVP is it's quite old, but it's not widely deployed. There are some deployments, typically in enterprise or aggregation networks, but we'll come on to MPLS traffic engineering in a minute, and that builds on this protocol. So the MPLS data plane has its origins in a belief that we couldn't do sufficient IP address lookup at line speed, which has turned out to be a false assumption. We're perfectly happy to forward IP traffic at ridiculous line speeds because the silicon got much better. But along the way, some other uses for MPLS came along that were pretty handy. It's based on a little header that's inserted on top of the IP packet and constructs a forwarding state based on a label lookup. So at every hop, you look up the label, and that tells you what interface to send the packet out of and put a different label on. And then along it goes through the network. It's creating a connection-oriented packet switching technology. And that turns out to work really well for traffic engineering. What MPLS traffic engineering does is use constraint-based shortest path first, where the constraint is basically bandwidth. Find me the shortest path with sufficient bandwidth for this flow. And it allows you to place traffic in quite a sophisticated way in your network to reduce the cost, to make more efficient use of the bandwidth. So this is a CapEx saving, to ensure that you get the right policies, the right behavior for certain types of traffic. So again, it's really nice for emergency service traffic. You can find a really short path and make sure it's got high bandwidth reserved ready for it. And it's really useful for recovery or protection against failure. So you can set up a backup path. If there's a failure on the primary path, you can just shift all the traffic to the backup path. The ultimate goal, it turns out, for MPLS-TE is cost saving. And you can look at cost saving two ways. But principally, it's squeezing more out of a network. Right? The service provider has spent money deploying equipment. They want to get as much traffic running through that network as predictably as possible. There's some protocols involved here. What was done was to take the existing IGPs, which are advertising and reporting on the quality of the links in the network, and to enhance them with a little bit of extra information to report on the information and status of the TE qualities of the link. And again, bandwidth is the is top of that list. So the IGP on its own would say link status and metric. The TE extensions gives you the bandwidth and a TE metric. On top of that, there's a signaling protocol required to go and program the nodes in the network. And what we did was we took RSVP and made some additions to it so it was traffic engineering aware. And that means that those RSVP packets, instead of following shortest path first, they actually have an explicit path nailed into the control messages so that we can set up the flow for the LSP. And, oh, that's interesting. Let's just do that.
Okay, GMPRS is exactly the technique where I started my IETF. And we have already been demonstrated saying that the RSVPT and OSPFT they works and they save the cost. So IETF is really good at doing something like generalization and make the same philosophy applied everywhere. So for every potential circuit switching technology, this concept is generalized and to construct a label hierarchy on the lambdas, on the label packet, and also on the fibers. So this one is extended only from the MPRS, and in the 2RFs is very typical. We give the OSPF-T and our RSVPT extensions. And on the same time, we also develop the new protocols called LMP for the coordination between the physical links. And this is all distributed on the nodes, how the GMPRS is working. And then path computation. So when you have everything on the distributed manner, then there would be a problem on the vision, because considering each of the node, you can only have a restricted vision of the whole network rather than we have a global topology information. So it is requested that the routing and path computation function to be moved to a component or entity that can have the global issue to provide further optimization. So PCE is evolved in this way and now very popular and can be applied as a component or can be applied in application or a network node everywhere, as long as there is a need for the path computation function. So the earliest RFC 4655 specifies the functionality, but it can be embedded in any routers, in every routers, and to save the cost where you need it. And the second RFC in this page, 5152, provide a more advanced use case, that is the virtual POP use case, which announces the PCE domains can be interacted with each other. So in this shape, there can be the interaction between the ASBR, and there can be remote call to stitch the result of the path computation to form an end-to-end in cross-domain path. So there are the different kind of realizations of the PCE in the architecture. And historically, okay, a short note, when we call the historically, means it's something like 10 or 20 years ago. And here, because this is a previous technique, so this slide shows something that's 3 or 5 years ago, maybe. So PCE actually locates at wherever there is a need for path computation. The first scenario would be the LSR. The second scenario would be NMS. They already have this kind of functionalities, but they do not just use the PCE terminology to do that. But after that, when we have a PCE separated out as a dedicated server, there are also special configuration like the T database, like the RSP database, how many connections are in the whole network. These are all understood on the PCE server. And there are also different ways to interact with other kind of PCEs. And the opposite to a PCE is some kind of PCC, the client who requests for a path computation. And that is where the PCE protocol is designed for path computation interaction. And then we comes the topology aggregation, because of different components have different topology informations. From the perspective of PCC, the network is usually rather simple, and for the PCE, rather it's a big and more complicated topology information. So here the RFC 7926 provide a very typical examples for how the abstraction is done between the client layer network and the service layer network. So usually when you look into the operators or even look into the vendors, there is very large scalability networks, but the representation on the client side is really simple. So here, for example, we have 5 nodes in the server network, but on the client connections, it's only useful to see 3 of them, and you can just hide them to simplify the work of the client. So the abstraction layer resource can be either node abstraction, can be also link abstraction, and also just show the topology to the client. And given this kind of abstraction, there can be a future technique about the virtualization, which means something you pretend you have, but you really have in another shape. So previous page shows an example on how to simplify via the abstraction, but this one also shows another kind of variation. You can also multiply your networks in the abstraction layer and allocate them to different virtual networks to satisfy the requirement for different users. And this is nothing but a map between the physical ones and the virtual ones, but what you need is just a memory on how many you really have, and don't just overload your network. So there are different kinds of policies, different kinds of algorithms working on how to efficiently virtualize and how to make best use of the abstractions. If you do it with a very abstracted manner, it will actually sacrifice your efficiency because you have too little information. But if you have maybe one-to-one mapping and show the whole picture, then the complexity of the client is really, really high. So there is always a balance between the degree of virtualization, and that introduce different kind of policies. BGPRS.
So one of the challenges is that the network understands its topology, its shared information, and we now need to export that information to some controlling computation entity. And we may, as Hamian has just said, need to abstract that information before we export it for policy reasons, for privacy reasons, to give customers or customer networks a specific view. So we identified that need, and we were looking for what protocol shall we use to do that, and picked BGP. And I think there were a number of reasons for that, and only one of those reasons was that the vendors driving that work happened to be really interested in BGP. BGP implementations are really good at applying policy. So abstraction is all about policy. So that's a good reason. BGP is actually quite good at moving bulk data around, and the export of topology is an example of moving bulk data. And it also turns out that the places in the network that you want to do the export from are typically nodes that are already running BGP. And lastly, a feature of BGP, the route reflector, allows you to send the information to multiple places without overloading the network nodes themselves. So we invented link state BGP, BGP-LS, and it's a set of encodings to take information that describes links and nodes in their traffic engineering form from the network and send them out in BGP. Two important notes on that. BGP is just a protocol that could do it. There's also work now to write Yang models to describe topology. We have a slide on that much later. And you could be using netconf to export topology. And there's also a proposal for using the PCE protocol. So we've seen how the PCE protocol goes between nodes and a controller. Well, maybe you could also use that to export topology. So there ends the first lesson, all of the stuff that's pretty much out there already. And now we're going to come on to new tools or work in progress. A lot of that is minor tweaks to existing protocols. For example, there's work out there to add a description of link latency into the IGPs so that when you collect the whole topology, you can see how much latency each link is adding. And I've seen all sorts of other things like some quality of reliability of the link will be reported. So lots of small tweaks, and then a number of somewhat larger pieces of work that are going on that we will introduce here. So the first one is improving IGP flooding, and this has been talked about in the IETF for the longest time. The intention is to reduce the processing load in the network as the IGPs continue to announce and maintain the network state. Particularly important is when there's a link failure, that information has to get propagated to everybody. If you can reduce the background processing of the IGP, maybe you can get the network to converge faster. This is interesting for traffic engineering because not all nodes in the network need to know about all TE-link changes. So if you can reduce the flooding of that information to only the people that need to know, you can make some savings. It might, however, actually not be necessary. And this is kind of work that's being discussed still, because when you do a TE-link advertisement, you're supposed to damp that advertisement anyway. You don't need to announce a change in bandwidth of 3 bits per second. You can bulk that up and say, well, maybe I'll only announce the change if it amounts to more than 10% of the bandwidth. Additionally, traffic engineering state has a tendency to be fairly static. So maybe there's no need. On the other hand, it could be interesting work. It's one of those things that we will play with. DETNet, deterministic networking, is a relatively new working group in the IETF. It's about building deterministic paths, predictable paths for data. It's aimed at layer 2 bridged and layer 3 routed network segments, quite often looking at a concatenation of those. So you might start it in layer 2, do some hops there, then move into a layer 3 network, and then pop back out into a layer 2 network. The intention is that the paths provide some predictability in terms of latency and loss and jitter. So not necessarily controlling those things, but knowing what the worst case might be. And that is really useful in delay sensitive networking for things like video transfer, especially popular for video editing suites. Probably quite useful for augmented reality, unless you like falling down holes. The work is being split between the IETF DETNet working group and IEEE 802.1, their time-sensitive networking working group, which is looking at the layer 2 parts of this. It's still a little early to know where this is ending up, but it looks like it's doing data plane encapsulation for MPLS and IP. It's relatively simple, although not completely trivial, and ends up based on tunnels, with the MPLS tunnels placed with some knowledge of network behavior, and well, that could well be RSVP-TE. As you see, this is the first box that doesn't show an RFC but shows an internet draft. Segment routing. Segment routing is essentially a tunneling technology. So the payload data is encapsulated in a packet, and it's forwarded based on information in that encapsulation header in a way that is very similar to IP source routing. That is to say, there's a list of hops placed in the packet header. Those hops describe the route that the packet must take through the network, and each packet is then a free agent. It goes off with its information in it. It doesn't follow any programmed path in a control plane. Each packet contains all the information it needs to get to the end. That makes it a traffic engineering technology, where some entity can compute a path it wants the packet to go on, program that information into the packet header, and off the packet goes and follows that path. So if the control entity is capable of seeing the whole topology and accounting for bandwidth, you can do a fairly sophisticated traffic engineering resource reservation protocol. The control plane, all the signaling is now not needed in a network, so there's great save there. The routing protocol continues, discovering the topology, and just has a little bit of augmentation to support segment routing. And segment routing works for MPLS and IPv6, and because it's a modern protocol, it does not support IPv4. Anyone shocked by not supporting IPv4? Good.
Okay, and given this kind of technologies, and then it's time to talk about how the controller is designed and what kind of techniques can be used via the controllers. So PCE, as previously discussed, it include functionalities on the path commutation, and this is exactly one of the functionalities need to be achieved by the controller in the SDN architecture, software-defined networking. So PCE protocol actually provide a very mature solution to the SDN southbound interface solution, and this kind of control and computation may also be applied on the single node. So the applications can be is proposed from both MPLS, non-packet, and IP environments. So this is widely used as a controller and can be constructed as a controller hierarchies if necessary. And based on this idea, we have promoted a new architecture named as ACTN, Abstraction and Control of TE Networks, by constructing the controller of the hierarchies. So this is actually some kind of state of art in the industry, and we are implementing this kind of SDN controller hierarchy to make use of the abstraction techniques. And this is very well accepted by the carriers for multi-domain interop and for multi-domain, multi-vendor interop and multi-domain coordination. So we separate the different list of the controllers, and from the customer, from the carrier, and from the vendor. So the customer usually do not have much knowledge on the network, and they only take care of a few boxes located in their working area. So what they need is just to represent their request to the carriers by a corresponding interface. We name this as a CMI. And the carrier is actually the critical component in the whole architecture, because to the above, it needs to be connected with the customer to understand their demand, and to the bottom, they need to interact with the vendors on the detailed network configuration. So to interface on them for the customer understanding, virtual service coordinating for the different customers, and the coordination between multi-domains for among the vendors. And this is all supported by the abstraction and the virtualization techniques. So the vendor-specific ones is actually the most complicated ones. It's very challenging because the scalability of the network, and there is a lot of parameters need to be configured on both the network level and the device level. So currently, I think most of the vendors have their own advantages for their own implementation, but people are still requesting for a standard interface to enable the interoperation among the multiple vendors. This is done on the MPI interface, and carrier can handle that in a multi-window case. So typical scenarios for ACT and how the topology is discovered, how the topology is abstracted and this page shows an example on how this is done. So if we look into the network number 1 domain, there are actually 7 nodes in the domain, but to be abstract, we only use the border nodes to form a 4-point topology and report it to a higher hierarchy of the controllers. So on the perspective of the MDSC, it will receive the topology information from 3 different domains and stitching them together to form a very brief topology that can be used and understood easily by the controller, by the customer controllers, which is the DC in here. And everything can be represented as a connectivity matrix to have local information and on the capability on the switching and the bandwidth information of the network. So everything is understandable from the abstraction topology. And given this kind of topology, people are capable to deploy their connections onto the networks. So we still assume there is a request from a cross-domain connection, and this request comes to the carriers first, and then it's decomposed into different windows and prospective domains. It is worth noting that this can't be a kind of technology-specific domains, saying that we have different techniques like IP and like optical, like something together. But everything is nothing but a kind of decomposition. As there is already a kind of standardized interface and models, we can easily instruct saying which domain to complete which part of the work. And this will be very helpful on the setting up the end-to-end tunnels and deploy the connections. So on the different level of interface, we are having different kind of protocols. So for the above interface, the demand is usually represented by the Young model and using the REST-CONF protocol. And for the negotiation between the operator and the vendors, there are multiple ways, including the PSAP and the REST-CONF Young, which is fully automated. There are also QX, CORBA, and SNMP used for many years, and but some kind of manual works requested. And for southbound interface, there can be PCE protocol. This is between the controller and the node, and among the nodes, there can be GMPRS also. So ACT has good progress in IETF. It was first proposed maybe 4 years ago, 2014, and directed to TIS working group in 2015. And in 2016, we did develop 2 hackathon events and then promote the drafts adopted in the working group. And our hackathon also evolved from transport only to IP plus transport. So that is a kind of demonstration of how the interoperation can be achieved via standard models. And now it's becoming an RFC. So the architecture is now stable. And what we are investigating on is a kind of Young models fit into this architecture. So before the listing of the Young models, we spend maybe 1 minute on introduce what is the Young model. So it's just a kind of data model that represents the information of the networking. And the most special one is the Young model is both human readable and machine parsable. So the readable for human make it easy for the developers to implement and interop. The machine parsable actually guarantee the efficiency, and that is why IETF finally chose the Young language to be the language for modeling. And currently it can be encoded as both XML and JSON format. And we are having more and more Young drafts in recent IETF meetings. And it is becoming a very key component for the whole system. So here we try to summarize how many young models need to be involved in the whole architectures. There are many, and we may still miss something, so don't be angry. And besides the two at the top is just the generalized draft for the ACT, and the bottom ones are actually drafts that describes how the network information is modeled, or how the model is used in the whole architecture. So each of the box in the chart is actually a module, a young module, and they located in separate drafts, and the arrows here shows the relationship on the modules. So who the arrow pointed one will augment to the base model, and this allows people to generalize the model and augment it for the technology specific use. So from the basic categorization, it is classified into topology, tunnel, service, and types. And we also have the layer 0 technology to layer 3 technology for every type of this kind of model. Oh, we are coming to the end as a summary session. So TE, traffic engineering, is really a valuable tool. You do not need to spend more money on your infrastructure, but you get more from your network. So it helps people to guarantee their quality of the delivery, and it also provides some kind of bonus on their networks by carefully and efficiently use their network resource. And to achieve this goal, actually, this is still an ongoing work, and there are really a lot of work in the past and at this moment. So most of them are widely deployed, and we are developing more tools and techniques. So there are lots of opportunity to be involved here if you understand, if you are experts on any layer of the technologies and want to bring such kind of models, highly welcomed. And this page just shows some pointers, but yeah, IETF started 30 years ago when I was born. So one page should not be sufficient to list all the reference, but the key RFCs has been listed in each of the previous slides, and you can look into that one and figure out that will help you to point to more RFCs. And some interesting working groups for the existing technology promotion, including the Ts for the architecture of all the TE technologies. And MPRS TE is something specially designed for MPRS. CCAMP is something specially designed for optical switching. And the PCE is everything about the PCE protocol. So Spring Working Groups is now working on the segment routing, and IDR works for the BGP and the BGP LS extension. NetMod is the right working group to do the young modeling and the corresponding protocols. And LSR provides the extension to the IGP. StanNet works on the time-sensitive networking. And I think that's all. So, right time for the questions, and you're welcome to provide us the feedback by doing the survey.
Perfect. I did warn you that it was going to be a squeeze to get it in an hour. I have a 4-day course I can teach exactly the same material. I think the next session in this room doesn't begin for 30 minutes, so we'll hang around and answer any questions if you want. Otherwise, you can go and find somewhere where the air conditioning actually works.
Just a native question. you have introduced the PCE, and before you have the distributed T protocols. My question is, they are the totally two different side of the protocol. One is a totally different way, distributed way, and the PCE is a totally centralized way. Is that true?
Yes, and I think when you reach some advanced age like me, you've seen this swing backwards and forwards in the industry multiple times. IP is very focused on being distributed. SDN is very focused on being centralized. Traffic engineering needs a centralized view, and we are moving backwards and forwards between centralized controller with a distributed control plane or totally centralized controller with a southbound interface. And there are pros and cons of those, for those. So discovery maybe works better with a distributed control plane. Rapid provisioning maybe works better with a central controller. Single point of failure really is bad for a single central controller. So there are pluses and minuses, and some of it is just fashion. Some of it is always liking to invent something new, but different operators have different use cases and different requirements.
Can I further? Is there any possibility that we can combine these two solutions, in some specific use case, or is there already this kind of work? Like the edge computing, right? We have the centralized control, and we also have some distributed way, and they can benefit each other.
Yeah, and I think one of Hamian's pictures for ACTN shows centralized controller talking down to a domain controller. Now, whether that domain controller then uses individual southbound programming or uses a control plane in that domain, nobody further up the stack knows about that or needs to know about it. So different domains can do different things, but still be underneath the central control architecture. Good. Run away.